We can look at one more. X approaching infinity. So we've seen that L'Hopital's rule applies in cases where we have indeterminate forms, 0 divided by 0, infinite by infinity, and just all avoiding division by 0 and many other forms. So it helps us go about derivatives that are difficult using other ways. So what's the natural log of infinity? So it's much better to understand this if you know how to sketch. So this is the way an exponential function behaves. So the natural log is actually kind of like the opposite, more like the diffraction. Cuts one on the x-axis, the other one is on the y-axis. So you see that still, even as you're approaching infinity as well, it's also going towards the infinity, right? This is the natural log of x. It's also going, as you go towards x values increasing, it's also going up, but at a slower rate compared to the exponential. So we're going to have infinity over infinity, which will still be undefined, so we can differentiate. Now, how do you differentiate the natural log of x? Okay, so we have to differentiate the top part and then also apply the same concept to the denominator. So what's the derivative of natural log of x? So we're going to have 1 over x over 1, which is just going to give us 1 over x, right? So we can just say the limit is x approaches 0. It's actually infinity. X approaches infinity for 1 over x. Now you know that whenever you're dividing, whenever it's bottom heavy, you know it's basically going to be approaching 0, obviously, right? So you can even know how this graph comes out. As you get to infinity, as the numbers get to increase, you get closer and closer to the x-axis. Okay, so therefore we can just say 0 is the answer. If we add x on top, you know it's infinity as a result. So this is basically, these are the use cases of the L'Hopital's rule, and I hope you've understood.